So I know Heikki for a long time now because he have 25 years of experience in distributed stationary and mobile controls. He's working as a CTO at TK Engineering in Finland, and he's a part-time postdoctoral research fellow in University of Tampere. And he had been involved in this CANopen standard for more than 15 years. And he is also involved with several research projects related with the multidiscipline products, managing processes starting from model-based design, ending to the field service and actions and generating changes. And I think today he will show how he can implement those generating changes in his GUI. So please, Heikki, take the screen.
Yes, thank you. Yes, my topic today is to present how to automate workflow of generation of, let's say, troubleshooting and system monitoring user interface for CANopen systems. And yes, why diagnostics is so important. And when I'm talking about diagnostics, I'm mainly focusing on, let's say, off-road special vehicles and working machineries and so on. Typical of those systems is that the life cycle is quite long. And there's not only manufacturing and production, but there's quite a long operation and field support phase. And that's why diagnostics is quite important over the life cycle of the systems. Of course, starting from prototyping and also integration testing, end-of-line testing in production, but mainly troubleshooting in the field during the long period of full operation. And traditionally, machine automation companies has put quite low effort on onboard diagnostics because traditionally it has not been considered so important, mainly due to tradition, because of course end users has been demanding better and better diagnostics. And old-fashioned discrete instrumentation has been a bottleneck quite a long time, but along CAN and CANopen systems, technology has not been obstacle anymore. And field buses provide quite excellent basis for systematic onboard diagnostics. And of course, the higher productivity demands are, let's say, focused to the operating companies of those machines. Then the requirements are coming to the system integrators and tool and device vendors. And tradition has been that this diagnostics development has been more or less neglected because each change in the rest of the design most probably has some effect to the diagnostics also. And whatever effort can be removed, that has been done. But the maintenance effort may be quite significantly reduced by introducing some design automation. There we have brought automated or computer-aided questions into the map, because during this system design, there's possibilities for systematic information reuse here and there. And information should be reusable because there are certain key information which is shared among different disciplines, or let's say adjacent process phases are using same information. Of course, different but still similar kind of projects need to be share information. And reuse is not 0 or 1 question. It can be utilized at any scale, which makes sense. And of course, validation is important, so that we should be somehow able to validate that certain design phases has been completed and error checks and so on shall be done. And what is also important is to reduce human mistakes. That's why design automation or computer aids for designs are quite welcome. And then productivity can be improved by, of course, at the first stage by improving workflows, but also automating and simplifying tasks, and then optimizing graphical user interfaces where applicable. And they are applicable mostly where some information shall be put into the design manually. And in our research and development, we have defined tool policies so that we are not intentionally limiting tools to be compliant among or inside each category. Of course, certain tools may have restrictions by themselves, and that's why the usage may be reduced, but we are not intentionally willing to reduce. And we have, of course, concentrated on the use of leading edge tools, of course. That's why we are using them also in the proof of concepts. And we have tried to avoid, let's say, large monolithic legacy tools, because they are always a problem due to the missing openness. And of course, we have focused on the use of open source freeware tools whenever it's applicable, because that enables a small company to utilize maintenance forced by many experts. And there's also important thing in avoiding commercial risk and lifecycle risk due to the consortia-based tools. And when the interfaces has been built between the tools, we are relying on either standard interfaces and de facto interfaces or formats when standard interfaces either are not existing or are not supported by the other tools. And then we have concentrated on, I would like to say, the glue logic or glue tools, combining those big tools together by means of plugins and extensions. And all glue applications we have implemented are, of course, following this principle and operating system independent. And then let's take a very brief look at the CANopen system design process, which is defined by CIA 306. Main idea is that component vendors provide device capability information as EDS files, and system tools are taking EDS system or component descriptions in as EDS files, and then use DCF files for component instance by instance configuration storage. And node list file is defining from which component instances the entire project consists of. That's enough right now. Of course, if we are using application programmable devices, we can utilize CANopen profile databases for component-based design of EDS files. But in this context, it's most important that yes, CANopen defines proven design process, which we can rely on. And of course, because the process has been well defined and also information storage formats has been logged, it's quite easy to implement reuse paths. And reusability is quite important, even in the basic design, because in the practical design work, there are, let's say, demands to do, let's say, last-minute changes and updates in the areas where the proven process-oriented toolchain may not be available or usable. So it shall always be possible to make some quick updates and fixes to get the projects done. And that's why also the workflow and tools should support or should be oriented to enable reusability. And of course, it's up to the system integrators when to use reuse features and how. And that was everything just put into the same figure regarding the CANopen system project. And why should we be so interested in this? You will see here. By using all flavors and important connectivity features of this, application interfaces can be managed in conjunction with the CANopen design. Node interface descriptions may be managed in the component-based way. Everything can be mapped to the system architecture. Then we can automatically get communication description for analysis purposes. We can get device configurations for assembly and service. Quite useful things. And of course, very well-defined core process enables us to supplement that in the model-based design for rapid control prototyping or target system deployment. And of course, using model-based design still enables us to use reuse paths here. And using this kind of design process with model-based connectivity enables us to concentrate the core IPR to the system model and supplemental hardware in the loop simulation, quite comprehensive parameter management and development of control behavior in the productive way, and also comprehensive device monitoring, signal status monitoring. But what's missing is status visualization, which shall or traditionally had to be developed manually. And finally, when we have standard output from the design process, we can utilize the standardized output for system monitoring with the analyzers, device assembly, which means configuration and software download by, let's say, CANopen level standard tools. And what we have both developed, used, and published before, we have evaluated generation of diagnostics interfaces automatically, but there has been some bottlenecks. Of course, we have been relying on de facto data sources, mainly the standard CANopen project files. And we have been able to generate the user interfaces where the system status visualization applies. But main problem is that there's no workflow support, there's no reuse path, and what is most problematic, there has not been any user interface for adjusting screen coordinates. And let's say when we are looking at the development of system monitoring user interface. Content of standard CANopen project, which consists of let's say node list file and corresponding DCF files. They define member components of the system, but not the installation order of those. That's why we had to bring electric design into the same picture, so that we can parse the device installation order out of the schematics, which is shown on the right side of this slide. And of course, main questions or main thing to be solved has been that we need reference designators, which has traditionally been long time in the electric design. And when we brought them into the CANopen design, we got a tool for combining CANopen design and schematics. And then, of course, because CANopen project, we are not capable of carrying screen coordinates and other kind of location information. In one research project, we developed a GraphML-based system description file, which can efficiently carry that information. And good thing of that file format is that it's actually intended to describe graphs, which means nodes and interconnections between them. That was perfect match with CANopen networks. And of course, when we were investigating that, of course, GEFI is de facto editor for graphs, but it has some missing things. And also Inkscape is quite heavyweight open source freeware editing tool not supporting GraphML. So there were need for dedicated process tool anyway. And this is a screenshot from GEFI. It provides quite nice user interface for managing the system structure, but there's no support for background image, which is a significant disadvantage. And then we started to think about that there's no sense to develop editor. It's too heavy, but luckily SVG is, as an image format, it's quite close to GraphML, depending on the viewpoint. And that's why we implemented conversion tool, or let's say process tool, which temporarily transfers GraphML to SVG, opens it into the editor, and after editing, transfers back to GraphML and stores to the original source. And I would say that semantically, this conversion is quite unambiguous. There's almost one-to-one relation which can be found between the certain elements. And of course, because both formats are XML, there are quite excellent management libraries. Only the editor side needs some care. And SVG, it's semantically not unambiguous because it's not dedicated for structural description. It's more oriented for representation of vector graphics. But it's accessible by generic XML libraries, no problem. And also, I would say that major vector graphics tools are supporting SVG, so that was quite natural choice. And this is how the same system layout looks in the Inkscape. after automated transformation from GraphML to Inkscape or into SVG. And luckily, Inkscape supports also editing of raw XML structures and element attributes, as well as Gephi. So this was quite win-win. And what was very nice, SVG, or especially Inkscape, enables description of device-to-device interconnections as rubber bands. So this is really device screen coordinate editor. And then, because we need anyway certain management depending on the editor we want to use, and there's also a workflow issue. When we first time generate this kind of system monitoring view, we don't have in the beginning valid screen coordinates at all. So whatever we edit at the first round, we anyway need to store them back to get some initial point for screen coordinates. And when we do next phases, next iterations, we will most probably reuse the existing coordinates and maybe introduce just minor modifications. So this very simple wrapper tool can take care about GraphML to SVG and back conversion. And regarding the background image, we can also bundle in format conversions from any format to PNG. And in the case of, let's say, device export to the device implementation from PNG to whatever. And quite intuitive layout management with support of default coordinates. But without such a tool, everything should be taken care of manually. First, save changes to the node list GraphML, and then to be able to use default coordinates, save the same information into another dedicated file. And without any wrapper tool, the use, or let's say automated or easy use of editor capable or supporting other than GraphML is quite problematic. And there's no support for background image. So we will manage to put majority of the necessary extra work into the simple wrapper tool. The result is that when we take, or we can also reuse, we can even in the iEC programmable display, we can do in the iEC code, coordinate edits, and then bring them back to the GraphML format. And the entire management looks like this. On the left side, there's again standard CANopen project output plus electric schematics, and then transformation to the GraphML file, then editing either GraphML itself or via SVG file, and then bidirectional connectivity to iEC 6.11.31 programmable displays. And what we have here, we have de facto data sources, CANopen project and schematics. Then we have workflow support. All boring and risky actions are managed by dedicated software. We have implemented reuse systematics. We rely on efficient editors, and the system status visualization is very easy to produce and maintain. And then, as a reminder that everything or many things can be integrated as an integral part of the CANopen system tools, just like we have used CANopen, just an example. And such tools make some magic when every time when we click save, and they have make lookalike procedures where we can bundle some global procedures to help or increase the overall efficiency. And typically such tools support also device-specific shortcuts, which can be described as CIA 306 Part 3 tool integration interface. And then some concluding remarks. We have had generation of full communication abstraction quite many years, including signals, parameters, and with meta information and emergency management. And now we brought into the picture also system status with screen layout management. And we can combine there not only the device and interconnection monitoring, but also emergency decoding. And we have proven that CANopen has excellent support for this kind of design tool integration, design automation, because everything is modular and supporting distributed control systems. And the interfaces are open enough so that interaction is quite easy with the other disciplines. And because CANopen is open, also the interfaces are open, and quite many tools are open. And what's important, we can support model-based design, which is a mega trend in the machine design. And we don't see any obstacles for applying the same procedures to the other bus systems. And for the future, we have detected some main problems, and the biggest obstacle seems to be in 3D mechanic design, because raster images can be exported quite easily, but the design culture in 3D mechanics design is not supporting the use of reference designator by default. So the architecture mapping needs special efforts. And another problem seems to be in the iEC 6.11.31 development interfaces, because iEC program code can be imported, exported easily, but communication parameters are not easy to import and export. And that was my topic today. Thank you for attention.